Good day everyone, this is Moe Shahram and this course is Physical Science Survey PSCI 10, and today we are going to talk about chapter 6 about electricity and magnetism. So we will cover electrical charge and their properties and talk about what are the forces involved in electrical charges and how the charge is transferred from one object to another. And then we will talk about the charge mechanism flow in different material such as conductor or semiconductor or superconductor or insulator. And then we will talk about how charge communicate their existence with another charge. So we talk about electric field, and then we talk about electrical potential, which we know as voltage. And then we will discuss how the charges actually behave in a given circuit. And we talk about simple circuit and the laws that govern and relates voltage, current, and resistance, which is Ohm's law. And then we talk about circuits such as series circuits and parallel circuits, and then discuss what are the different forms of current. We have direct current and we have alternative currents. So we cover that, and then we move on to concept magnets and magnetism. Discuss how the magnet came about, discovered, and what are the sources of magnetism, why some material are magnetized. And then we talk about how Earth is magnetized. And then we talk about magnetic force and the magnetic field and magnetic induction, and how we can generate a magnet by applying a current in a piece of wire. And from there we talk about the concept of motors and generator as a result of a very interesting law which called Faraday's laws of induction. And then we'll talk about how we transport electricity from one location to another. And then we conclude with the concept of electromagnetism and the concept of light. Let's go ahead and begin with electric charge. We have seen evidence of electric charge in lightning, electricity, and sometimes we touch a doorknob and we get a zap. We will talk about our electrostatic concept, which deals with static charges and charges on different objects, and they're pretty much static and are not moving. But later on we talk about what happens and how can we move charges in different material. So electrostatics basically involved with electric charges that are not moving, and they distribute themselves on surface of conductors, and they also have some sort of a field around themselves. Just like when you open a bottle of perfume from a distance, you can smell that perfume. In analogy to if you have an electric charge, it has a aura field around it which other charges can actually sense. So we will talk about that in more detail. Most objects are electrically neutral, but they all have electrical charge within them. Atom has electric charge inside, but overall they are neutral. And the reason they're neutral because the electric charges are balanced inside them. And electric charge is a fundamental quantity, just like mass or length or time that we mentioned earlier. Those are the fundamental quantities in physics, in nature actually. We can characterize them, we can model them, and we can use them to our benefit. Things that actually are very useful to us, things like electrical motor, computers, cell phones, and everything else that we use pretty much today. We have two types of electric charge. We have positive and negative. The positive charge is associated with the proton. The smallest positive charge is a charge of a proton, and the corresponding smallest negative charge is charge of electron. Those particles, proton and electrons, are fundamental particles. Put them together, we have an atom. But the atom, under normal circumstances, is neutral. So the number of proton and number of electron in the atom are the same, and therefore they cancel each other. Of course, we have another particle called neutron, and that is not electrically charged. However, neutrons are within the nucleus of atom, but if you manage to isolate a neutron, it quickly decays to a proton and an electron. In fact, it consists of a positive and negative charge within the neutron. So when it's isolated, it disintegrates to a positive and negative charge. And we know that proton and neutrons are much massive than electron. In fact, about 1800 times massive than electron. When we look at the charges and relative mass of these, we can see that proton, we designate that with the P and a plus to indicate it's a positive charge, and its mass is 1.673 10 to the minus 27 kilograms. So if we assign 1 to this amount of mass, then the mass of neutron, it's pretty much the same as the proton. Very small difference here between the two. However, the mass of electron, it's much smaller, as we mentioned earlier. So it's 9.1 10 to the minus 31 kilogram. As far as their charges, the electron has a negative charge. We assign a negative charge of electron, -1. And then with proton has positive and neutron has 0 charge. We know that, and we can experimentally verify this, that these charges have some sort of a force between them. We will discuss that in a minute, but Coulomb was the first to actually assign an amount of charge to an electron. He calculated that if you have this many electrons, 6.25 10 to the 18 many electrons, we can assign a charge of 1 unit, 1 coulomb. The unit of charge is called coulomb to that many electrons. If that many electron is 1 coulomb, then the charge of 1 electron should be 1 over that, which is 1.6 10 to the minus 19 coulomb. As you can see, the charge of 1 electron is very small. You need that many electrons to have 1 coulomb charge. Sometimes we have objects or collection of particles that have a charge. We show that with the Q. Again, we see that charge of proton is 1.6 10 to the minus 19 coulomb. Charge of electron is minus 1.6 10 to the minus 19 coulomb, and charge of a neutron is 0. A neutral atom is also have 0 charge. Another thing that is important, we have an integer number of charges, or one object that has 5Q, that means 5 times this number of negative charges. These charges can attract or repel each other. So there is a force involved between them. And that force is a Coulomb force. We call it a Coulomb law. We see that the like charges, whether they are positive or negative, they repel each other. And unlike charges, they attract each other. Remember, we had the gravitational force between two masses when we had the, let's say, a mass 1 and then a mass 2. We had the gravitational force. There was a force, and then there was a constant of G, and then we had mass 1 times mass 2 divided by distance between them squared. Now here we have two different scenarios, attractive and repulsive, whereas in the gravitational force was always attractive. Laws of charges, obviously, like charges repel, unlike charges attract. Neutrals, they don't have any attraction except the gravitational attraction. In the case of a Coulomb force or electrical force, the Coulomb force is equal to some number, some constant, times a charge of the one particle times charge of the second particle divided by r squared. So you can see the resemblance and similarity, but there's a lot of differences too. For one thing, this constant k is totally different than this constant g. The unit of force obviously is the same. The unit of force is Newton, and that doesn't change. So Newton here and Newton there. The unit of charge is Coulomb, and the unit of distance is the same. If you look at the unit of the k, which is the electrostatic constant, because k from here is equal to F times r squared divided by Q1 and Q2. The numerator we have the Newton, and then we have meter square r squared divided by Coulomb squared. Okay, that's where that unit comes from. One similarity between the two is 1 over distance squared, and this is called inverse square law, and it shows itself in several different phenomena in physics and in nature. It means that the force changes as 1 over a square as distance increases, so it reduces. When you have an object that has more negative charge, we call that object is negatively charged, and if it has more positive charge than negative, we call that positively charged. Okay, just like an atom, if you take away an electron from an atom, that atom becomes a positive ion. If you add an electron to an atom, that atom becomes negative ion. So let's answer this question now. According to Coulomb law, a pair of particles that are placed twice as far, Q1 here and Q2 here, and then you move them twice as far, Q1 here and Q2 here, what happens? Experience force that r. So look at these answers here. It's 1 over r squared. So r, if r is twice, so you would be 1 over 2r squared, and that would be 1 over 4r squared. So it would be 1/4 as strong. Two charges are initially separated by 1 centimeter. How far away must they be for the electric force between them to be 1/4? We just did that previous question. If it is 3 centimeter, 3 centimeter square is 1/9 squared, and the 4 centimeter 1 over. So here are some recap of electrostatic force versus the gravitational force. Obviously the equation look similar, but they have different parameters. They both share, or they both have the inverse square behavior. The Coulomb force is can be both attractive or repulsive, and the gravitational force is always attractive. In terms of strength of this, Coulomb force is much stronger than gravitational force. Or we will talk again about 4 fundamental forces of nature. You will see that the relative strength between the Coulomb force and the gravitational force is huge. We talked about that gravitational field cannot be shielded. So no matter where you are, you always are under some gravitational field influence. So gravitational field cannot be shielded. However, the electric field can be shielded. So if you have a metal container, the inside doesn't have any electric field. Once we have an object charged by electric charge, we know that the electric charge can be transferred from one object to another. You do this all the time. When you walk on the carpet, you rub against the carpet, and by just rubbing against that carpet, you are acquiring charges from that carpet. And charges can be easily taken away from one object or another, because these charges are on the surface of object. By rubbing a plastic against a wool, you can actually transfer charges. As you can see, there are 4 mechanisms for transferring charge. One is by just rubbing or friction. The other one is that by just making a contact, you can transfer the excess charge from one object to the other one. Or by induction, you don't have to touch an object that is charged. As long as one object is charged, you can bring that near another object and you would induce charges in that other object, or by polarization. And we'll see the examples of all of that. Let's look at this animation. As you can see, just by rubbing your foot on the floor of a carpet here, you are acquiring these negative charges. And those charges distribute themselves on the surface of your body quickly, okay? And you may have experienced this. When you try to touch the knob, you get a little zap. That's basically charging by contact and friction. Take other examples, such as a piece of glass and a piece of silk. You just rub the silk on the glass, you can actually take the negative electrons on the surface of the glass into the silk. Your glass becomes positively charged. If you take different material, say rubber and a wool, and you rub it against each other, or negative charges from the fur transferred to the piece of rubber here, and you have the rubber negatively charged. As you will see, if you have a balloon which is a plastic, you can rub against your hair. If you have a long hair that is dry and clean, you can transfer charges from hair into that balloon charge. You don't see the charges, but you can do other experiment to recognize their existence, their sign, whether they're positive or negative. We use a very simple device called electroscope. It's just this piece of foil that is folded. You can have, for example, a piece of aluminum foil and just bent like that, and then connect it with the metal. Now, if you charge your plastic or PVC pipe or a piece of rubber, and you bring that near this, because this is negatively charged, it actually induces the charges on this piece of metal. In other words, it pushes back the negative charges further down to this, because this is a conductor, down to this piece of foil. Now, the negative charges, obviously, they repel each other, right? And they accumulate on this foil, and then you can actually see that this foil will start to separate, and that's an indication that there is a charge accumulation there. So this is called charge by induction. Now, another example is when you have lightning. How does the lightning happen? Well, we know that clouds are made out of water droplets, also dust particles and atoms and molecules in the air. Some cloud has more negatively charged particle than the other one. The wind moves them around, they rub against each other. And what happens when they rub against each other, some part of the cloud becomes more negatively charged and another part becomes more positively charged. So now the clouds would have what we call it a net charge. These clouds move around, and when they get close to some objects on the surface of the earth, what they do, they induce again this negatively charged cloud moving around and gets close to these objects. It pushes back the negative charges on that object and make the tip of these objects more positive. And guess what? Now you have more positive on the tip of these objects and negative charges on the cloud. They attract each other, and that attraction, when it gets close enough, it shows itself as a lightning. You can also charge a material by polarization. How do you do that? Well, again, every object is made out of atom. Atom has electrons and protons in the nucleus and so on. And then if you bring an object that is heavily charged, say positively charged here in this case, near another object, it attracts the negative charge towards it because it has that field around it, and it communicates that says, hey, there's a positive charge here, and all the negative charges would want to be close to it. But if you don't touch it or just bring close enough, what you have done, you have actually made this other object polarized, because one side of this object is negatively charged and the other side is positively charged. So this is a polarization. And this is a good demo and example that you can also do it at home. So take a balloon and rub it against your long hair. Now your balloon is negative charge, so you go and place it next to a wall. Because your balloon is negatively charged, it's going to push back all the negative charges on the surface of the wall, and that way you're left with a lot of positive charge near it. And guess what? Now this is more negatively charged, this is positive, so they kind of attract each other. But the charge doesn't get transferred in this way. It just stays there. So that's why the balloon gets stuck on the wall. So let's look at this animation here. You can see that if I don't show the charges, let me just show no charges here. You have a sweater, a wool sweater, and you have, or your hair, you have a balloon. So you just rub that against this and you bring it near the wall and you see the balloon stick to the wall. So what's happening? So let's now look at the charges. Let's do this again. Normally your sweater or your hair is neutral because they have same amount of positive and negative charges, and the same thing for the balloon, same amount of positive and negative charges, and same thing for the wall is neutral. So when I go and rub against this, I'm taking a lot of these negative charges and make this negatively charged, and obviously it gets attracted to the positively charged. And now when I bring here near that, look what happens. I'm polarizing the wall. See, the negative charge repels the negative charge, and then if I stick it to the wall, it's going to stay because now all these negative charges are pushed away, and I'm left with a lot of positive here and a lot of negative there, which they attract each other, so they stick together. And this is called charge by polarization. Now, as you saw, the charges that you take away from the sweater all gets into the balloon. You're not actually destroying any charges, or you're not creating any charges. The net charge between these two objects is constant. It's conserved. Charges are conserved. That's very important. Now we talk about what materials can charges move through. Well, charges can move easily through conductors. Now, conductors are mostly metals, and they can easily let the charges move around. electrons to move around. The atomic size stays where it is. They can, oscillate in place, but the electrons can, between these atomic sites, wander around. Not that easily, but they can jump from one atom to another, and then the other one jumps to the vacancy, and then the other one jumps to the other one, and so on. Some fluids can also be conductive. If you have ions, in the fluid. Now, plasma is very conductive because they have both positive and negative charges in there. Then you have another class of material that's called insulator. In this case, the electrons are so tightly connected to the nucleus of the atoms in there that it's not easy to move them around. So they don't move around that easily. As a result, they don't allow electrons or charged particles to conduct. That's called insulator. Then we have another class of material that are semiconductors. Now, semiconductors in a pure state, they are actually insulator. They don't conduct. For example, a good example is silicon. Silicon, in a pure state, it's not conductive. And I'll show you why it's not. Then another class of materials called superconductor. These materials are very conductive, and unlike these normal regular conductors, which electrons move around with some difficulty, but in superconductor they have easier time to move around because these superconductors are kept at low temperature and the atomic sides don't vibrate or oscillate as much, so they let the electrons to kind of move around easier. There are good applications for those. So let's discuss each one a little bit more detail. Conductors, such as a good conductor is silver, a good conductor is copper. So copper, for example, has 29 electrons, and it happens that the outermost orbit or shell of the copper has an electron that can wander around from one side to another easily. If you look at a copper wire, you can see the atomic side, and you can see that valence electron can move around and jump around in a random fashion. Same thing for other metals such as aluminum. If you have an object which is metal or conductor, if you add charge to it, what happens to those charges? They very quickly distribute themselves around the surface of that conductor. If the conductor shape is uniform, that charges kind of distribute uniformly. However, if the shape is not uniform and has a sharp edges, corners, they distribute themselves a little bit different. It's not as uniform. Why is that? Because, say you add a lot of charges on top of this sphere. Because the sphere is uniform, all these charges, as they distribute themselves, they push each other away because they're same sign, right? Kind of distribute themselves. But when you get to an object like this, which has a sharp corner, the or like charges, the positive charges here, they push each other away in a uniform manner. But when this positive charge gets here, there's nothing on this side. They kind of accumulate more on the corner because there is not much force from this side, say from this side pushing that charge away, or from this side pushing this charge away. And therefore you have more accumulation of charges on the sharp corners or sharp bends. The repulsion on the corners are kind of weaker, therefore allow for the charges to accumulate more on the sharp corners. Now, let's talk about insulators. As I said, the atomic structure of the insulators, such as rubber, plastic, glass, or pure silicon, as I mentioned earlier, they have all their outermost electron are tightly bound to the nucleus, and they cannot be taken away that easily because of electrostatic force, Coulomb force between the electrons and nucleus. They help each other pretty tight. So let's take the silicon, for example. Now, silicon has four valence electrons at the outermost shell, outermost orbit. And we're going to talk extensively about the shell and orbit in next chapter. When they are in the form of a crystal, they kind of share these electrons. So they all, if you look at any silicon atom, they have 8 electrons outermost shell. And we will see that when you have this 8 electron, the atom is very happy and it doesn't want to do anything. They doesn't want to give up their electron, or they don't want to take any excess electron. That is an insulate. The electrons cannot move around unless you do something here. Unless you take one of these silicon atoms and put another atom that has an extra electron there, and that's where you have semiconductor. Semiconductors in pure state are usually not conductive. They're insulator. But when you add an impurity, for example, we take one of these silicons and put a phosphorus. Now, phosphorus has 5 electrons in the outermost shell. And what happens, then you're left with an excess electron in that orbit. It's kind of an orphan. It doesn't have a place, so it can easily be moved around. And we will see how that happens shortly. When this impurity is introduced to this piece of silicon, we call that a N-type silicon because it has an extra electron there. It's a kind of a negatively charged. That electron can jump to another place that has another phosphorus somewhere here, out there. We introduce enough impurity so that these electrons can hop around between these impurity states. So you have an extra electron near this impurity, which is phosphorus. Then you introduce another impurity to another piece of silicon, which we call the p-type, or maybe boron, for example, which has 3 electrons in the outermost shell. So there is a vacancy there. Guess what? If you bring these two next to each other, this electron could easily be moved to that vacancy. And once you get the electrons moving, then you have a conductivity, motion of the electron. That's how you make a p-n junction. That's how you make a transistor, that you can control its conductivity. When you want it to conduct, when you don't want it to conduct, based on a little bit of a push you give to this electron to go there or not to go there. Okay, we'll talk about that in more detail. Then the other class of materials is superconductor, and which have pretty much a very, very low resistance to motion of the electron. And they basically, you can have them in the form of a wire or a strip of wire and so on, and have a very interesting application because, as we will see later, once you have a very low resistance, almost zero resistance conductor, you send electrical current through it, and as a result you can have a magnetic field generated. We will see that shortly. Strong magnetic field. These are usually made out of different multi-atom crystals, and you can see that at the low temperature, resistance to motion of electron is very, very low as compared to let's say copper resistance. This and it increases as you increase the temperature. But as you can see here, these up to a certain temperature, they practically have no resistance. But if you increase the temperature, then they obviously become resistive. Now we talked about this field around electric charges. The electric charges have what you call some sort of an aura around them, which sends a message to the outside that, hey, I am a negative charge and have so much charge. And that is called the electric field. Now, the other electric charge also sends that. So if it's a positive one, it sends a certain electric field. And if it's a negative, it sends an electric field, and they can recognize each other. As soon as you have an electric charge, you have electric field around it instantaneously. So electric field travels at the speed of light. How do they look like? Well, we can represent them in the form of line. So if you have a positive charge, we can represent electric field as arrows that are emerging out from the positive charge. If you have a negative charge, we can represent them with arrows that goes into the charge. So that's the difference. So the electric field of a negative charge, it's inward towards the charge. The electric field of the positive charge, it's outward away from the charge. Now if you put a little charge here, it's going to feel that. So it's going to be pushed, if this is positive, pushed away in this direction by this charge, and is going to be attracted in that direction by that charge. Now if you put it here, it's going to be attracted this way by this charge along this electric field. Now if you put it here, it's going to be pushed away by this charge, and then when it's pushed away, it's going to be attracted by that charge. So you see how it works? The field between charges, if it's positive and negative, it looks like this. It comes out from the positive charge and goes into the negative charge. Between them straight, positive to negative. Now if you have two like charges, in this case two positive ones, the field between them, they push each other away. So the field lines are diverted. So let me see if I have a animation for that. All right, here's my positive charge. I can move them around. And here's my negative charge. Okay. Yeah, I can put another positive charge here, but let's just do one positive charge, one negative charge. And then let's show the electric field. So you see the electric field? It looks like that. Now if I take this away and put another positive charge here, they kind of don't like each other. If you want to measure the amount of electric field, let's just put this away. I have one charge here, a positive charge, and this is a tiny little charge that can sense how much the force. As I get close to it, you see the force increases drastically. As I go away, it reduces quickly as 1 over r squared. You see that? I can show the value. You see? And if this is a negative charge, the force is, because this is a tiny little positive, it goes towards it. All right. So when you have this kind of situation, you have a positive and negative, you usually call this a dipole. Two poles, dipole, okay? Positive and negative. Now, the Coulomb force we talked about is equal to some constant, electrostatic constant. These constants are obtained by experiments and take two charges, move them around in different location and find the force between them, and you notice that you can actually get the same number for this constant and verify that over many experiments. Say now charge Q1 is going to feel a force because of the Q2. So Q1 feels a force due to the electric field of the Q2. You saw that animation. So I put that little charge, it felt the force because of the other one. And the amount of force that its own charge, times that electric field that is there. If we do that, then we can just find E is equal to F over Q1. Okay? Electric field is equal to the force over the charge. We can find that electric field, right? So the electric field due to charge Q2 is equal to K, because you just divide this whole thing by Q1, so you get Q2 divided by R squared. Okay? That's how you find the value of electric field. It should be field, not filed. All right. Now, we can actually do experiment in the lab with something that generates a lot of charges, This device is called Van de Graaff. It generates a lot of charges. You plug it to the outlet, and there's a belt that kind of brush away charges from the bottom and puts it on the top dome. This dome here is a metal dome. After a while, it has a lot of charges on it. And if you touch that dome, all those charges goes into your body, including your hair. Now your hairs are loose. What happens? The charges accumulate on your hair, and then because they're the same charge, the hairs are pushing each other away. So now you get your hair and looks like this. Obviously you have to have some insulator under your foot, otherwise all charges can go through you and the metal conductor through to the ground, and you're going to get a good shock. So sometimes in some courses we do this demonstration in the class. Now let's ask you a question here. Suppose you're in a class and then your phone may ring and you want to avoid that. So where would you hide your cell phone? Would you hide it in some metal can, a metal container here, or in a thick plastic container so that you don't hear the ring? In fact, we can demonstrate this in the lab. Here, you can try this at home. Have your friend call you and choose two container, one very thick rubber container and one metal container, and you see that in the insulating rubber you would hear the ring, but when you put it in the metal container you don't hear anything. Why? Because you have insulated the electric field. When somebody calls you, as you will talk more detail, the electromagnetic waves reaching your cell phone, and your cell phone starts recognizing that electromagnetic field with that signature or frequency and coding that contains in it, and it starts ringing. If you shield that electromagnetic field by metal, then that electromagnetic field doesn't reach it. Another question is that suppose you're out there and it's a stormy night and it starts lightning, and lightning can hit anything. We just show you how it happens. So you have three options: under the tree, inside the phone booth, the glass phone booth, or inside the trash can. Where would you hide? Again, same principle. Lightning is a lot of charges there. It can actually go through the tree, burn the tree and whatever is under it, or it can go through the glass and whatever is inside the phone booth, but it cannot go through the metal. So if you hide in a metal can, you're safe because it's shielded. All the charges distribute on the surface of the metal and then get dissipated to the ground, but nothing goes inside. What happens when you have a charge in an electric field? Well, it gets influenced by, right? So how does it get influenced by? What we learn in gravitational case, you have one mass here and you have another mass here. They're attracted. It depends to their distance, and as you move these masses away from each other, you are building a potential energy. Just like when I mentioned that if I have my pen moved from the surface of a table up, I am building a potential energy with respect to the surface of a table. So there is a gravitational potential energy built between my pen and the surface of the same phenomena happens when you have charges. So if you have a charge, and let's say you have a negative charge here and you have a little tiny positive charge, and you move this away from it, you are building electrical potential energy. Okay? The electrical potential energy of a charge against another charge depends on the distance between them. Same analogy again. Suppose you have a mass that you raise this mass through this pulley by cranking this lever here, it goes up, so therefore you have built potential energy. Now if you cut the rope, that potential energy turns into a kinetic energy while this mass is being attracted down towards the ground. Same phenomena in the electrical. You separate a positive from a negative, and then you let go because you built the potential energy. It's gonna bang crash to the negative charge with some kinetic energy. What have we done here by separating these two charges? We have done some work. In the charge case, we separate these two charges because they want to attract each other. Now that's also true for two like charges, because like charges you push them together. Okay, that's the work you do. Same thing in this case, when a positive and negative are separated, you do some work to separate them. You have actually converted work to electrical potential energy. Remember concept of the work? Work was force times distance. We learned that earlier, right? Now force, in this case, in case of electrical charge, we just showed that force was equal to what? Force was equal to charge times electric field. Now where that electric field is? Electric field is between the two charges. Remember I showed you the picture of the from positive to negative? So there is electric field right there between the two. The work therefore is equal to electric force, which is Q times E times D, which is the distance. This work is potential energy, is electrical potential energy. So we have pretty much parallel situation as we talked about earlier. We have a little definition for when you multiply the electric field, let me do it with a different color here, times distance. We show that with the notation V, and we call that voltage. So that's the concept of voltage. Has another name, electric potential, not energy, electric potential. Work was electric potential energy, and that was equal to Q times E times D, which I showed you here, and that is defined as Q times V, which is electric potential. So there are two different things. You have electric potential energy, okay, which is, we showed with U, which is equivalent to work, and then you have electric potential, which is the voltage. We show that with V, okay? So that is a definition of voltage, or another name for it is electrical potential. You know that a battery is 9 volt. That's its electric potential. It has that potential. So when you talk about 1.5 volt battery, or if you talk about 110 volt outlet, that is its potential, electric potential. Voltage. Voltage is the amount of work it would take to move a charge between 2 points in electric field, divided by the value of the charge, or electric potential energy divided by Q. So relationship between volt and electric potential energy is V is equal to U divided by Q. What is its unit? Well, it's energy per charge. Energy unit is joules, we know that. The unit for charge is coulomb, we know that. We call that volt. Joules per coulomb is called volt. Here, remember, we had the balloon, we have a whole bunch of negative and whole bunch of, you build up a voltage, huge voltage. This could be a 6,000 volt, and yet that's not dangerous. The reason is not dangerous because there's not enough charges there. So you may have a very high voltage but small amount of charges, and that's not dangerous. What is dangerous is when you have a high voltage and a lot of charge, as we're going to talk about how that affects us shortly. Some questions for you. Electric potential energy is measured in joules. Electric potential, call that voltage, is measured in unit of volts. So let's see how these charges move through the conductor. Now we have a piece of conductor. That piece of conductor could be a wire, a copper wire. you put a battery which is 1.5 volt electric potential or voltage. So there is a 1.5 volt between this side of the battery and the other side of the battery. So there's a potential difference between the. So batteries represents a potential difference, and that's measured in volt. Once you do that, then electrons starts moving, because electrons wants to go towards the positive. Because they're negative, they want to go to a positive. Let's look at this demonstration here. What's going on here? This is a positive side and this is a negative side. The electrons are starting moving from here, going through this part and getting to the other side, to the positive side. Let's say we have a resistor here, something that doesn't allow electrons to go as easily. So they're going to bump around here and go through with some difficulty, some resistance. Now if I reduce the resistance, it just goes as smooth. But if I increase the resistance, it has a harder time to go through it. That is what happens when you have a potential difference between the two sides of a conductor. The electric charges starts moving. It's analogous to container that has water. It has more water on one side and less water on the other side. Very quickly, all these water are going to find their way. Eventually, all have the same level or same potential, so they level off. If you want to keep the level of this side higher than the other level, what you do? You just keep taking the water from this side and pump it to the other side. What do we do electrically? Well, that's what battery does. Battery takes the carrier from this side and pushes out to the other side so that it keeps the potential difference or voltage constant. Of course, batteries ran out. Now, if you have the battery that you could constantly charge, that would process continues. That's what battery keeps the potential difference from one side of this conductor to the other side. And that's what causes the flow of electric charge. Now, how does this electric charge flows? How quickly or how slowly? It's the rate of flow of charge that we will call that a electric current. Charge is moving in time. Say certain amount of charge moving in certain amount of time. We define that as an electric current. Obviously, when you connect the battery, one side positive, one side negative, the positive side is a high potential, the negative side is a low potential, and that causes a current to flow. And later on we will see that there is a different type of current. This type of current called a DC current. Electrons move from negative side to the positive side. But there are other types of current that oscillate. We talk about that extensively. Definition of electric current is the rate of electric charge flowing in time, or in case of the AC current, oscillating in time. What is the unit of this? Well, we know the unit of charge is coulomb. The unit of time is second. Coulomb per second, we have a name for it, amperes. Sometimes we show it with A, sometimes we show it with AMP, or spell it out. Which of these statements is true? Electric current is a flow of electric charge. Electric current is stored in a battery. Nothing is stored. Battery basically has a potential difference, pushes the electric charge to go through the circuit. The current is not stored. Let's do an example here. Let's say we have a wire that carries I, let's say I is equal to what? 0.5 amperes, and in time of 2 minutes. How much net charge goes past point in the wire in this time frame? What we know, I is half an amp, T is 2 minutes, so we need to convert that to seconds, so that's 120 seconds. and we want to find out what charges. But we already had equation. Remember, I was equal to Q over T. So from here, Q is equal to I times T. I, which is the current, 0.5 amp times 120 second. So that's 60 coulomb. And then how many electrons make up this amount of? So remember, we said one electron has a charge of 1.6, 10 to the minus 19 coulomb, one electron. But now we have what? How many coulombs? We have 60 coulombs. 60 coulomb. So 60 coulomb divided by this, that gives us 3.8, almost 4, 10 to the 20 electrons. That many electrons. Now, batteries come in different forms. You've seen all these batteries, this type, or use this type of batteries, or car batteries, or batteries for, home. All of these are basically producing a electric potential, and they're measured in unit of voltage, probably 12 volts. Bigger cars, they have 24 volts. These things are 3 volts, 1.5 volts or 9 volts. The outlet is 110, sometimes 220. You can even make a battery out of fruit that is acidic. Well, these batteries, they have acid in there, and then you put two different types of electrode in there, and that causes the migration of charges through the acid, which is conductive, and then create a potential on one side with respect to the other side. So if you have a copper and a zinc and you insert that into a lemon, keep a distance between them, you'll see that you have a voltage or electric potential built. You probably have about 1 volt built on this. We can make that actually. And if you put a whole bunch of them, you can get even 4 or 5 volts out of it. Put 4 or 5 of these lemons in series. Now, we talked about current and flow of current in the conductor, but the current doesn't go that easily. Each conductor has a resistance, as we talked about. What does that resistance depends on? Well, it depends on few factors. What material that is made out of? That is the resistivity, we call that rho, depends on the type of material. Resistivity for silver is less than resistivity for aluminum, or less than resistivity for copper. Then the length of that conductor or a wire, and the cross section of that, how thick that is. These are the factors that depends on the resistor of that conductor. The analogous situation is that if you have a kind of a inclined plane here with a lot of pegs in there, and you drop a ball, these balls to kind of find their way down, and they collide with these different pins here until they get down here. So these pins or pegs are causing a resistance. Same thing happens in the piece of conductor or a wire. All these electrons are trying to get through to the positive terminal or positive high voltage, and they collide with each other, they collide with atomic sides, but eventually they find their way to there. Now let's look at this animation here. If you look at the resistor of this piece of conductor, I can change the material. If I increase the resistivity, the resistor goes up. If I reduce the resistivity, the resistor goes down. So that's the one-to-one relation. Now, then I can change the length. If I change the length, increase the length, the resistor goes up. That's a direct relation, right? It makes sense. If I reduce the length, the resistor goes down. And what about the area, cross-section area? If I increase the cross-section area, that means I allow more carriers or electrons to move around, so I have less resistance. If I make the wire thin, I have a huge resistance. So the thicker the wire, the less resistance. The thinner the wire, the more resistance. And we kind of call that wire gauge. All right, for example, gauge 12 be more resistive than gauge 1 or 2 or 3 or 4. Now we are in the position to look at a simple circuit, because now we know we can build a potential difference via a battery, for example, and then we can have wire, which is a conductor, allows the motion of carriers easily through it with a small resistance. And then we can have some load, things like a fan or a light bulb or a speaker or what have you. With a switch you can turn it on or off. When you turn off the switch, you disconnect the circuit, so the carriers or current doesn't go through it. Rather than drawing these things all the time, we kind of use symbols for simple circuits. A switch looks like this. Battery shows with two lines, one larger than the other one, is a positive and negative, and the wire is just line. And the light bulb or a load, we can show like that. For resistor, we show like this. Instead of this light bulb could be just a resistor. And later on we have capacitor. Capacitors are like this. Okay, two parallel line, but both the same size. Again, when we have a battery and we have a circuit enclosed, the carriers starts going from the negative to the positive. That would be the electron flow. However, there's a convention that the direction of the current, we say it's the opposite to the direction of the electron. But in reality, it's electrons that are moving in the circuit. We just assign the opposite direction of the motion of the electron to be the direction of the current. So let me see if I can show you this animation here. So let's watch this. Here basically shows that how the electrons move through a conductor. You see these tiny little dots? Those are the electrons. This is the path of the electron. And these circles are the atomic sites in that particular conductor. All right, so now here there's a switch. Okay, here is the battery, and here's the light. Okay, and as the wires are connected. So you see the electrons are moving, drifting towards the positive. And if there is no potential, they just wander around from one side to another. But once the potential is high, they start moving all towards the positive side. Okay, now we get to a point that we can talk about the relationship between these parameters that we learned. We talked about voltage, we talked about current, we talked about resistance. How do they relate to each other? Very simple. And that was discovered by Ohms, and it's called Ohm's law. The relationship is very simple. The voltage is equal to current times resistance in a circuit. So if you know what the current is, if you know what the resistance is, you can know what the voltage is across that potential. Or if you know what voltage is and you know what current, you can find the resistance. You have all these three options here. So V is equal to IR. This is when you know this and you know that, you find V. But if you want to find current, you must know what V is and what R is. And if you want to know what resistance is, you need to know what voltage is and what current is. So these three represents Ohm's law. Voltage has the unit of volt, current has a unit of ampere, and resistance has a unit of ohms. We call it ohm. Volt divided by amp, it's called ohms, and we show that with the omega, or we write ohms. In any circuit, you have two of these variables, you can find the other one. And here's the animation for that. Now let's see what happens if we reduce the resistance. The current increases. So we have here, we set about what, let's start with 1.5 volt. And now I can change the resistance and my current changes. So less resistance, more current, more resistance, less current. All right? Or if you have a, say, fixed resistor here, let's put this right there, and I increase the voltage, my current increases. So you see how it works? You can use this animation to try it yourself. So let's ask this question here. When you double the voltage in a given simple electric circuit, you double the, now notice, you have a circuit, okay, and here's the circuit, and let's say there's a resistor here, and if you double the voltage, so if this is V, if you do 2V, what happens? What changes here? R is going to be fixed, and we know V is equal to IR. I is equal to V over R. If make V 2V, R being the same, what happens? So it would be 2I is equal to 2V divided by R. So you doubled the current. Now let's take a break at this point, and then we come back and talk about different circuits.